Welcome to Math 201, our lesson on section 4.7, L'Hopital's rule. We're going to talk about properties of limits. So recall that if you want to take the limit as x approaches c of f over g, you can take the limit of the numerator over the limit of the denominator, right? So the limit as x approaches c of f of x over the limit as x approaches c of g of x. So that was a property of limits from way back at the start of the semester. So what did we do in the early part of the semester if we take these two limits, the numerator and the denominator, and they both went to zero? Okay, so this one goes to zero, and this one also goes to zero. So in that case, back when we studied limits, it just meant we have to do more algebra, right? We had to manipulate the function, the f over g, until you could plug in your c and not get 0 over 0. Okay, let's look at a limit. The limit as x approaches 1 of x to the fourth plus 2x minus 6 over 7x squared minus 4x plus 3. The first thing we always try with limits is to just plug in the limiting value, in this case 1. So if I plug in a 1, I get 1 to the fourth plus 2 times 1 minus 6 over 7 times 1 squared minus 4 times 1 plus 3. All right, so that comes out to 1 plus 2 is 3. 3 minus 6 is negative 3. And 7 minus 4 is 3. 3 plus 3 is 6. And I get negative 1/2. Okay, so that's the reason you always try plugging in first, right? If you can plug the value in, then that's the easiest way to evaluate the limit. If you plug in the limiting value and you don't get something undefined, like if you don't get 0 over 0 or infinity over infinity, then you're done. You got the answer. Okay, here's another example of a limit. We're going to do this one two ways. So first thing we should always try is to just plug in the limiting value. Plug in the value x is approaching, in this case 2. So if I plug that in, I get 3 times 2 squared minus 2 minus 10 over 5 times 2 squared plus 3 times 2 minus 26, which is 12 minus 2 minus 10 is 0. And 20 plus 6 minus 26 is also 0. Okay, 0 over 0 is an indeterminate form. And earlier in the semester, we learned how to solve these by doing more algebra. You need to simplify what you're taking the limit of until you can plug in x equals 2 in this case and not get 0 over 0. So I'm going to do some factoring and canceling. So I'm going to write this as the limit as x approaches 2. And then my numerator can factor to 3x plus 5 times x minus 2. And the denominator factors to 5x plus 13 times x minus 2. The x minus 2's cancel, so we have the limit as x approaches 2 of 3x plus 5 over 5x plus 13. And now let's see what happens if I try to plug in a 2. I get 3 times 2 plus 5 over 5 times 2 plus 13, which is 11 over 23. Not 0 over 0, so I have an answer, 11 over 23. So we can do factoring and canceling. Now I'm going to show you a new method. Okay, you get 0 over 0, right? So if I try to just plug in, I get 0 over 0, which means I can't just plug in. So what I'm going to do is I'm going to use something called L'Hopital's rule. I'm going to write LR anytime I use it, so that I know I can remind myself what I did. And L'Hopital's rule says that if you get 0 over 0 or infinity over infinity, the limit will be the same if you take the derivative of both the numerator and the denominator. Okay, so if I take the derivative of the numerator, I get 6x minus 1. The derivative of the denominator is 10x plus 3. And now what happens if I try to plug in the x equals 2? I get 6 times 2 minus 1 over 10 times 2 plus 3. which is 11 over 23, right? Same thing I got up here, 11 over 23. And this is called L'Hopital's rule. Here's another one we can look at two ways. So I did this is the same function as earlier, 3x squared minus x minus 10 over 5x squared plus 3x minus 26, but now x is approaching infinity, not 2. So if I try to just plug in infinity, this is infinity over infinity. So infinity over infinity when you just plug in, which is an indeterminate form. So I'm going to do a fancy trick here, and I am going to multiply the top and bottom of my fraction by 1 over x squared. So I have the limit as x goes to infinity of 3x squared minus x minus 10 over 5x squared plus 3x minus 26. And I'm just going to multiply by a fancy form of 1. And that fancy form of 1 is going to be the form 1 over x squared. 1 over x squared over 1 over x squared. And then I'm going to distribute that 1 over x squared to the parentheses on the top and the bottom. So I get the limit as x approaches infinity. So 3x squared times 1 over x squared is 3. X times 1 over x squared is 1 over x. And 10 times 1 over x squared is 10 over x squared. And then I'm going to do the same thing on the bottom. Distribute my 1 over x squared times 5x squared, and I get 5. 1 over x squared times 3x is 3 over x. And 1 over x squared times negative 26 is negative 26 over x squared. And now when I try to plug in infinity, this term is going to go to 0. This term is going to go to 0. Because when denominators get really big, the value of a fraction gets really small. And it turns out to be 3/5. Okay, but it turns out we can also use L'Hopital's rule in this situation. In infinity over infinity situation, you can take the limit as x goes to infinity of the derivatives. Take the derivative of the top and the derivative of the bottom. So I have 6x minus 1 over 10x plus 3. That still goes to infinity over infinity, okay, which means I could do L'Hopital's rule again. So I'm going to take the limit as x goes to infinity. The derivative of 6x minus 1 is 6. The derivative of 10x plus 3 is 10. And the limit as x goes to infinity of 6/10 is 6/10 or 3/5. Same thing I got with the fancy algebra. So some terminology. If you're taking the limit as x approaches c of f of x over g of x, you take the limit of the numerator over the limit of the denominator, and you get 0 over 0, or you get infinity over infinity. Those limits are called indeterminate form. We don't know what the limit is, okay? We have to do more work to get the answer. L'Hopital's rule says that if f and g are differentiable, then the limit as x goes to a of f of x over g of x, if it's of indeterminate form, 0 over 0 or infinity over infinity, then you can take the limit as x approaches a of f prime over g prime, and that will be the same as the limit as x approaches a of f over g. Be very careful because this is not the quotient rule. You're not taking the derivative of the whole function. You're taking the derivative of the top over the derivative of the bottom to help you evaluate a limit. Right. To explain in layman's language why this works, if the numerator and denominator are both tending towards 0, for example, 0 over 0, okay, what matters is how fast they're going there relative to each other. So if the numerator is winning, if the numerator is going to go to 0 much, much faster than the denominator, the whole fraction will go to 0, right? Because if a fraction whose numerator is 0 is 0. So if the numerator wins the race, then the whole thing will be 0, right? If the denominator wins the race and the denominator goes to 0 fastest, then when a denominator is really, really, really small, the value of a fraction is really, really, really big. So if the denominator dominates and goes to 0 much, much faster than the numerator, the whole fraction will go to infinity. But the rate at which each of them goes to 0 it's kind of like a tug of war, right? So there isn't necessarily a winner. It might settle somewhere between 0 and infinity at some other constant. Okay. So what tells us how fast a function goes to 0 or a function goes to infinity is its derivative. Okay. So its derivative tells us how fast they are relative to each other. So that's why we can just take the derivatives and take the limits of the derivatives. Okay, here's an example. The limit as x goes to infinity of x squared plus 2 e to the x over e to the x plus x. I'm going to start by trying to plug in an infinity, and I get infinity plus infinity over infinity plus infinity, which is infinity over infinity. Okay, so this is an indeterminate form of the form infinity over infinity, so I can use L'Hopital's rule. Take the limit as x goes to infinity, the derivative of the numerator over the derivative of the denominator. So the numerator's derivative is 2x plus 2e to the x, and the derivative of the denominator is e to the x plus 1. Now, if I try to plug an infinity in at this point, I get infinity over infinity. So I can apply L'Hopital's rule again. Take the derivative of the numerator. The derivative of 2x is 2 plus 2e to the x. The derivative of e to the x is e to the x. The derivative of 1 is 0. So this is still going to infinity over infinity. So I do it again. The derivative of 2 plus 2e to the x is 2e to the x, because the derivative of 2 is 0. The derivative of e to the x is e to the x. My e to the x's cancel. So this is the limit as x goes to infinity of 2, which is 2. Okay, I'd like you to pause the video while you work through this next activity. When you're ready to go over it, come back and press play. Okay, the limit as x goes to 0 of sine x over x. But first, we just try plugging in 0. Okay, so we have sine of 0 over 0. The sine of 0 is 0. So this goes to 0 over 0, which means I can apply L'Hopital's rule. This is an indeterminate form, which means I don't know the answer. So I'm going to apply L'Hopital's rule. The limit as x goes to 0, the derivative of sine x is cosine x, and the derivative of x is 1. And now if I try to plug in x equals 0, I get the cosine of 0 over 1, which is 1 over 1, which is 1. Number 2, the limit as x approaches 1 of ln x over 3x squared minus 2x minus 1. So first thing I do is I try to just plug in x equals 1. So I have the ln of 1 over 3 times 1 squared minus 2 times 1 minus 1. The ln of 1 is 0. And this is 3 minus 2 minus 1, which is 0. So I have 0 over 0, indeterminate form. I can use L'Hopital's rule. Take the derivative of the numerator and the denominator. So the derivative of ln x is 1 over x. And the derivative of 3x squared minus 2x minus 1 is 6x minus 2. Try to plug in the 1 now, and I have 1 over 1 divided by 6 times 1 minus 2. So this is 1 over 4. Number 3, we're going to take the limit as x goes to infinity of x cubed plus 4 root x over 7x cubed. I'm going to start by just trying to plug in infinity, and I see that this is going to go to infinity over infinity. Right, so a big number cubed, this is going to go to infinity, this is going to go to infinity, this goes to infinity. All right, so that infinity over infinity is one of the forms where we are allowed to invoke L'Hopital's rule. So this is going to become the limit as x goes to infinity. The derivative of the numerator is 3x squared plus 2x to the negative 1 half. And the derivative of 7x cubed is 21x squared. Now, if I try to plug in infinity at this point, I get infinity plus 0 over infinity, which is still infinity over infinity. So I'm going to apply L'Hopital's rule again. The derivative of 3x squared is 6x. The derivative of 2x to the negative 1/2 is negative x to the negative 3/2. And the derivative of 21x squared is 42x. When I try to plug in infinity, I get infinity plus 0 over infinity, which is still infinity over infinity, which means I can do L'Hopital's rule again. So I'm taking the limit as x goes to infinity. The derivative of 6x is 6. The derivative of negative x to the negative 3/2 is going to be positive 3/2 x to the negative 5/2 over the derivative of 42x is 42. Now this goes to 0, and I'm just left with 6 over 42, which is 1/7. Okay, the limit as x goes to 0 of sine over cosine. Try to just plug in the 0 first. I get sine of 0 over the cosine of 0, which is 0 over 1. That is not an indeterminate form. 0 over 1 is just 0. No L'Hopital's rule was necessary for number 4. Okay, we're going to try to see if we can find a pattern using L'Hopital's rule for some functions that look like a polynomial over e to the x. So let's say I have x over e to the x and I want the limit as x goes to infinity. If I first just try to plug infinity in, I get infinity over infinity. So I apply L'Hopital's rule and I have the limit as x goes to infinity of 1 over e to the x, which is 1 over infinity, which is 0. Right? If your numerator is constant at 1 and the denominator blows up, a really big denominator, the value of the fraction is going to 0. Okay, let's see if I do the limit as x goes to infinity of x squared over e to the x. So if I try to just plug in infinity, I get infinity over infinity, so I can do L'Hopital's rule. And I have the limit as x goes to infinity of 2x over e to the x, which still goes to infinity over infinity. So I do L'Hopital's rule again. And now I have 2 over e to the x, which is 2 over infinity, which is 0. Okay, so now can you predict the following limit without calculating hundreds or thousands of derivatives? So I have x to the 2021 over e to the x. The limit as x goes to infinity. So I'm just going to, if I were to keep applying L'Hopital's rule, right now it goes to infinity over infinity. I could apply L'Hopital's rule over 2,000 times, but eventually the derivative of this numerator is going to be a constant. Eventually, the derivative of this numerator is going to be a constant. But the derivative of e to the x is always going to be e to the x. So eventually, when I apply L'Hopital's rule multiple times, this is going to be a constant over e to the x. And that limit is going to be a constant over infinity, which is 0. Okay, sometimes we need to be able to change the form of our indeterminate form. So not all limits appear in a form that makes L'Hopital's rule useful. Remember that L'Hopital's rule can only be applied if your function looks like 0 over 0 or infinity over infinity. So let's look at this example. I want to take the limit as x approaches 0 from the right of x times ln x. So x goes to 0, right? But the ln of x, as x approaches 0, maybe we'll remind ourselves what ln of x looks like. As my x values approach 0, my y values go to negative infinity. Okay, so 0 times negative infinity is an indeterminate form. Okay, so the values are approaching 0. These values are approaching negative infinity, indeterminate form. So I don't know what this product is. Like you might think that it's 0, but it depends on how fast this goes to 0 and how fast this goes to infinity. because multiplying things by something really small tends to make them smaller, but multiplying things by something really big tends to make them bigger. So we have a tug of war here between the things going to zero and things going to infinity. So instead of doing some fancy algebra to try to simplify this, I am going to rewrite x times ln x as the ln of x divided by, instead of multiplying by x, I can divide by its reciprocal. So we very frequently do this in the reverse, right? Instead of dividing by a fraction, we multiply by the reciprocal, but I'm reversing it. So instead of multiplying by x, I'm going to divide by its reciprocal 1 over x. And now when I try to plug 0 in, the as x goes to 0, ln of x goes to negative infinity, and 1 over x goes to infinity. So now I have written this in a way so that it looks like infinity over infinity, an indeterminate form where you are allowed to apply L'Hopital's rule. So I'm going to take the limit as x goes to 0 from the right. The derivative of ln x is 1 over x, and the derivative of 1 over x is negative 1 over x squared. And then I have a compound fraction. I'm going to, instead of dividing by negative 1 over x squared, I'm going to multiply by its reciprocal. So this is the limit as x approaches 0 from the right of x squared over x. That would reduce to just an x, and I've got the negative. So the limit as x approaches 0 from the right of negative x is 0. Okay, next up we have an activity to the L'Hopital visit. And so I want you to take a few minutes to try this, pause the video. When you're ready to go over it, come back and press play. The limit as x goes to infinity of x times the sine of 1 over x. So x is going to go to infinity. 1 over x is going to go to 0. So if the denominator is going to infinity, 1 over infinity goes to 0. So we're taking the sine of 0, which goes to 0. So I have an indeterminate form. Infinity times 0 is an indeterminate form. I don't know what the product is. So I'm going to try to rewrite it as an indeterminate form that looks like either 0 over 0 or infinity over infinity. So I'm not doing L'Hopital's rule yet. Right now, I'm just rewriting what's inside what I'm taking the limit of. So sine of 1 over x is going to stay. But then instead of multiplying by x, I'm going to divide by its reciprocal. And now when I try to plug in infinity, sine of 1 over x goes to 0, and 1 over x also goes to 0. So I can now apply L'Hopital's rule because I have an indeterminate form of 0 over 0. So I'm going to take the limit as x approaches infinity. The derivative of sine is cosine. So I've got cosine 1 over x. But then you also have to multiply by the derivative of what's inside. The derivative of 1 over x is negative 1 over x squared. And then the derivative of 1 over x, the derivative of the denominator is negative 1 over x squared. And I have this nice cancellation. And now I can just take the limit as x goes to infinity of the cosine of 1 over x, which would be the cosine of, if you let x go to infinity, 1 over infinity goes to 0. So the cosine of 0, which is 1. Use L'Hopital's rule in the picture below with graphs of f and g to find the limit as x approaches 1 of f over g. Note that you can do this without finding the precise expressions for f and g. You do not have to find an equation for the graph of f and an equation for the graph of g. So I want to take the limit as x approaches 1 of f of x over g of x. So if I look at my graph, as x approaches 1, f of x approaches 0, and as x approaches 1, g of x also approaches 0, right? So think way back when we first studied limits, okay? We have little ant marching along the graph of f. As the x values are getting closer to 1, the y values are getting closer to 0. Same for g. Okay, so it goes to 0 over 0. So that is an indeterminate form that allows us to use L'Hopital's rule. So I can take the limit as x approaches 1 of f prime of x over g prime of x. Okay, and f prime and g prime are the slopes of f and g. Okay, so this is the limit as x approaches 1. F prime of x, because f is a line, f prime is just the slope of f at every value. So the slope looks like rise is 2, run is 2. The slope of f is 1. Okay, and the slope of g, it looks like I've got a rise of 1 and a run of 2. So 1/2. So this is the limit as x approaches 1 of 2, which is 2. Okay, number 3, the limit as x approaches 0 of e to the x over e to the x minus 1. So if minus 1 over x. If I start by just plugging in a 0, e to the 0, that's 1. Um, so e to the 0 is 1, 1 minus 1, that would go to 0. And 1 over x, when the denominator gets really, really small, like 0.1, 0.01, 0.001, 1 divided by that is going to go to infinity. So right now, this is going to 1 over 0, which is infinity, minus infinity. So my numerator of the first fraction is going to 1 and the denominator is going to 0. So this whole fraction is going to infinity because numerator is going to 1. The denominator is getting teeny, 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 tiny. So the value of the fraction is going to blow up to infinity. Same thing here, 1 over infinity. So infinity minus infinity. That's an indeterminate form. Okay, it depends on which one's going to infinity faster. So we're going to start by finding a common denominator. Okay, so I'm subtracting two fractions here. A good first instinct is to add them, and to do that, we need a common denominator. So I'm going to multiply this first fraction, e to the x over e to the x minus 1 by x over x. So I'm going to have x e to the x over x e to the x minus x. And then the second fraction, 1 over x, I'm going to multiply that by e to the x minus 1 over e to the x minus 1. So I have e to the x minus 1 over x e to the x minus x. So I've got this common denominator. Now that means I can actually add or subtract the numerators. So this is going to be the limit as x approaches 0 of x e to the x minus e to the x plus 1. I'm distributing this negative sign to my e to the x minus 1. So that's why it's minus e to the x plus 1. And then dividing by the common denominator, x e to the x minus x. Now that I have a simpler fraction, I've subtracted the two fractions that I started with. Let's see what happens if I plug in x equals 0. Okay, so I have 0 and e to the 0. So that's 0 times 1, which is 0. So that goes to 0. E to the x goes to 1. So I have 0 minus 1 plus 1. And in the denominator, I have 0 minus 0. So that's 0 over 0, which means I can use L'Hopital's rule. Okay, 0 over 0 allows me to use L'Hopital's rule. So that means I can take the derivative of the numerator and the derivative of the denominator. Now, the derivative of x e to the x, that is a product. So I'm going to have to use the product rule on this. So I'm going to have f prime g. So it's going to be 1 times e to the x plus f g prime minus the derivative of e to the x is e to the x, and the derivative of 1 is 0. So that goes away. And then for the derivative of the denominator, I'm going to have the same product rule. I'm going to have to take the derivative of x e to the x. So it is going to be 1 e to the x plus x e to the x minus 1. And now if I plug in x equals 0, I'm going to have 1 plus 0 minus 1, which is 0. And then in the denominator, I have 1 plus 0 minus 1, which is 0 over 0 again. So I'm going to have to do L'Hopital's rule again because I have 0 over 0. So I'm going to take the derivative of the numerator and the denominator again. Okay, here's where we left off. I was taking a limit and I got 0 over 0 a second time. So I'm going to have to do L'Hopital's rule again. So I'm still taking the limit as x goes to 0, but I'm going to take the derivative of the numerator and the derivative of the denominator. So the derivative of e to the x is just e to the x. The derivative of x e to the x I know is f prime g. So it's going to be 1 e to the x plus f g prime x e to the x minus the derivative of e to the x is e to the x. So that's this one came down here. All right, and then I take the derivative of the denominator. The derivative of e to the x is e to the x. The derivative of x e to the x is 1 e to the x plus x e to the x. And then the derivative of 1 is 0. So that one, I don't have to write anything down. All right, to simplify, I've got some like terms in my numerator. I have e to the x plus e to the x minus e to the x. So that leaves me with just an e to the x. So I have e to the x plus x e to the x in the numerator. And in the denominator, I have 2 e to the x plus x e to the x. And now, if I try to plug in 0 for my x's, I get e to the 0, which is 1, plus 0 times 1, which is 0, over 2 e to the 0, so that's 2, plus 0, which is a half.